for some of you, your first interaction with the QRC. So let me be the first to welcome you to our first QRC event. We do not just seminars like this, but also we're here every week, Monday, Tuesday, Wednesday, Thursday for EI during the nighttime. So please feel free to keep using us as a resource. Does anybody know how to make appointments with the QRC? Maybe? No?
No, ma'am.
Okay. All right. Well, I'm going to give you a website right now that I'd like you all to go to and bookmark. So it's https://usaffa.mywconline.com. MyWCOnline, MyWCOnline.com. If you go there, it's going to ask you to register for an account. Okay, just it's going to ask some basic information, so your first name, last name, major if you have one, squadron, and then you'll be good to go. And then you can select QRC, and it's going to show you the schedule of everything that's coming up, who you can make appointments with for chemistry, calculus, engineering mechanics, physics. So this is going to be something you're not only going to use this semester, but probably next semester for Calc 2, probably for other STEM classes. So it'll also tell you what's upcoming for big group EI or seminars like this, but then also what the schedule is for appointments and walking hours. So that's where you're going to go for all of your wonderful QRC information. My name is Dr. Alyssa Ortiz. I am the main mathematics tutor down in the QRC. I also teach Calc 1 during M7. So I'm very familiar with what you guys are doing in Calc 1. And a certain assignment that's due in how many days? A couple, yeah, for some of you maybe a little bit longer, whether you're MRT day. So what this seminar is going to be all about is reviewing some of those major concepts that you will need not only to compute that or complete that assignment, but also these are going to be skills you're going to really be using in this course. And I'll try to point out when I can where you're going to be using the concept down the road, okay? So starting off, we're going to focus on finding the equation of a line between 2 points, and we're going to do that in a few different ways. Okay, so the first way is going to be if you're just given 2 points. All right, so this will be our first example. And you'll see the format, how this is going to go is I'm going to do an example of a type of problem, and we're going to go through it in detail, and if you have questions, please stop me, okay? We have 2.5 hours. That will be enough for questions, at least for some of you, maybe not everyone. That's what night 2 is for, so you can get even more questions answered. But there will be time for some questions, so if something's not making sense, please feel free to stop me. So I'll try to go through the first example in detail, and then I'm going to give you a little bit of time to practice a very similar problem, so that way you'll really know if you got it or not before we move on to the next type of problem. All right, so our point 1 is -1, 4. So our x-coordinate is -1, y-coordinate 4. And this is our point number 1. And our point number 2 is 3, -5. Okay. And we're asked to find the equation of a line. And I believe on your worksheet it actually asks you for the equation of a line in a specific format. Am I correct on that? Yeah, what is that format they ask for? Okay, y equals mx plus b. Okay, what does the m stand for?
Slope.
Slope, yes. So m stands for slope. And what is the b supposed to represent?
Y-intercept.
The y-intercept. Good. All right. Okay, what do you think the first thing we're going to look for is, the B or the M?
B.
It's actually always the M first, okay? There's a couple of different ways to do this, and I'll address both ways. Who's ever used the method where they try to solve for M and then B? Okay. Who's used something called the point slope intercept, or the point slope formula, excuse me? Okay, so there's two methods. I'm not going to steer you towards one or the other. I'm actually going to show you both. Okay, so whichever one kind of resonates with you more, that's the one you should stick with. All right, so, but either method does require you to find the slope first. The way we calculate slope is going to be change of y divided by change of x. Okay? Now it doesn't matter if you do 0.2 minus 0.1 or 0.1 minus 0.2. What does matter is that you're consistent, right? I can't subtract y2 minus y1 and then on the bottom reverse the order for x, right? So whatever order you pick, you have to be consistent in the numerator and in the denominator. Now I bet most of you probably do 0.2 minus 0.1. That's the usual, so I'll do that. Okay? So let's call -5, that's our y2. So the y-coordinate for the second point, and y1 is going to be 4, the y-coordinate for the first point. So we're doing y2 minus y1, okay, second y minus first y, divided by second x minus first x. So notice I did it in the same order, right? Number 2 minus number 1, and I didn't switch it. All right, so this is going to equal -5 minus 4 over 3 minus -1. And then we'll go ahead and simplify that. So the numerator simplifies to -9. In the denominator, we have a minus there, so we're really adding 1. So we're going to get a +4 in the denominator. Okay? Can that simplify any further? No. So our slope is just going to be expressed as -9 over 4. Now once we have the slope, like I said, there's two different ways we can go from here. One method is to go ahead and try to solve for b. The other method is to use what's called the point slope formula. I'll show solving for b first, and then the slope formula method second. All right? So the solving for b method would be to go back to this general form of our line y equals mx plus b and plug in the information that we know. Well, we just found m, so we could go ahead and plug in m equals -9 over 4. But we also need something to plug in for y and x. We want b to be the only thing that we don't know in that equation so we can solve for it. Now you can either use an x and a y from point 1 and use that to plug in for y and x into this formula, or you can use point number 2. It actually doesn't matter which one you use, okay? As long as you don't mix and match, right? So I can either use x and y from this point or x and y from this point. Let's go ahead and use the x and y from point number 1. Okay, so I'm plugging in 4 for y, and then for m, we're going to use what we just calculated, the -9 over 4. And for x, I have to go back to that same point that I'm using, so I'm going to use x equals -1. And then plus b, because b is the thing that we don't know. That's what we're trying to solve for. All right? So combining the negatives together, this is going to become 4 equals +9 over 4 plus b. And then to solve for b, we just need to subtract 9 over 4 from both sides. So b is going to equal 4 minus 9 over 4. And if we want to express that nicely as a single fraction, we're going to need a common denominator. So go ahead and multiply and divide 4 by 4. So we can rewrite 4 as what divided by 4?
16.
Good, 16 over 4 minus 9 over 4, okay, which is 7 over 4. Okay, so we know m, because we had that before. We just found out what the slope, or the y-intercept is, b. So we can go ahead and plug both of those constants back in, and we can have our line in y equals mx plus b formula. So y equals -9 over 4 times x plus 7 over 4. Okay? Find the slope and then go ahead and solve for b method. There's a different way. It's called the slope intercept formula. And I guess, so I don't have to erase, because I don't want to erase that yet. I'm going to go ahead and do the second method right here. Can you guys... Okay, I know at least one of you knows this. Okay, yeah, slope intercept formula.
Y minus y1 equals m parentheses x minus x1.
Perfect. Okay, now what is the x1, y1? What is that in that formula? One of the points. Does it matter which one you use? Nope. Okay. Well, since we used point number 1 for the first method, let's go ahead and use point number 2 just because. Okay. So our second point was 3 comma negative 5. So the 3 would go where in this formula? The x1. Okay. So basically, we're treating. Let me get another color real quick. Okay. So we're going to treat this like our x1 and this like our y1. Okay, for the purpose of that formula. Or you could have used the other point. So you could have used -1 for your x1 in this formula or 4 for your y1. Again, it doesn't matter which point you use as long as you don't mix and match. So let's go ahead and use the 3 comma negative 5. So we're going to get y minus -5. And then we have our slope, which is the -9/4. And then we're going to go ahead and plug in our x1 as 3. Okay. So, are we done? No, we're not done because you were asked specifically in your homework to put it in the format y equals mx plus b. Well, it turns out you can still get there from here, okay? What you have to do is solve for y, all right? So, what do we need to do to this equation right here to solve for y? Well, yeah, there's 2 things we need to do, okay? One thing, I heard it somewhere, is distribute the -9/4. Yes, we do need to do that. There's one other thing we need to do.
Divide by 5.
Not divide by 5. Okay, so this is going to be minus minus, so this side is actually going to become y plus 5 equals, and let's go ahead and distribute that -9/4. So -9/4 times x, so we get -9/4x, and then -9/4 times -3 is going to become plus 27/4, okay? Now what are we going to do with that 5? Subtract it. So subtract 5 from both sides. We get y equals -9/4x plus 27/4 and then subtract 5, okay? But that still doesn't look quite like the answer that we got before. How would we get to the answer we got before? Yeah, we have to combine these two into a single number. So this is going to give us y equals -9/4x plus 27/4. And how do we rewrite? Oops, that should be minus.
Minus 24.
Minus 20/4. Ah, now it's starting to look like what we expected. Okay, so we got to the same place. So sorry. We got to the same place 2 different ways. Okay. Raising. Thank you. You were totally right. Okay. Thank you. Not slope intercept. Definitely. Okay. I really appreciate you pointing that out. Through the points, -1/3, 1/2, and 4/3, 1/4. And I expect your final answer to be in that y equals mx plus b format. For you? Okay. So first step, of course, regardless of which method you're using, you should be calculating that slope. Calculators will simplify some of those fractions for you. This one in particular, yeah, -3/20 is not such a nice number. You're not getting step for you to check. So if you're the calculate B sort of person, these would be the steps. And I think I used, what did I use? I used the second point. If you use the first point, your math might look a little different. Okay. And then your final answer. Oh. See, that should go away in a second. Final answer, drum roll. Should look like that. Okay. If you are the point slope formula type, okay, then you would have a slightly different method. Okay, but you should get to the same place. So, anybody not get excellent. So, another way that you might see this, okay, is this is actually easier. Okay, so sometimes you're not given 2 points, you're actually given the slope in 1 point. Why would I say this is an easier question?
You don't have to solve because you already have the slope. So you
Yeah,
just have to
so
solve
that
for
took
B.
out some of your calculation right off the bat. So they already computed m for you, okay? And then from here, our slope is equal to -2, and our point is -1, 7. Okay? So point slope formula says we're going to take y minus the y in our point, which is 7, equals our slope times x minus, in this case, -1. So if we distribute the -2, we're going to get -2x, and then what? So this is really x plus 1,
Yes, ma'am.
okay? And then I'm distributing a -2 to that, so it should look like -2x and then -2. Okay? And then to be done, we just have to solve for y, so add 7 to this. Okay? And then combine the constant. All right. Well, those are much nicer numbers than the previous example. Okay? And our work was much shorter because we didn't have to solve for m. All right, so hopefully this one should go a little quicker for you, but go ahead and try that practice problem real quick, where you're given the slope of 1/4 and the point 1/2, 3. And again, it doesn't matter which method you use as long as the one that you're using you feel confident with. So either the solve for B method or the point slope formula method. Reveal. Okay, for the calculate B folks, this is what your algebra should look like. That's not a very nice number. And so then your answer would be y equals 1/4 x plus 23/8. If you're a point slope formula kind of person, then your algebra would look something like this. All right. So now we know how to calculate a line if we're given 2 points, or calculate the equation of line if we're given the slope in just 1 point. So one last kind of twist on this line equation type problems would be, okay, where it's a little bit more abstract, but sometimes the more abstract a question is, the easier the calculation part is. So it's a tougher logic or thinking type of question, but easier on the calculation. In fact, I don't think I'm hardly going to have to write anything for this example. Okay, so we know that our line goes to the point 2, 4, and the only other piece of information we're given is that our line needs to be parallel to the x-axis. What does that mean?
0. Has to be horizontal.
Has to be a horizontal. Yeah, that's basically what it's telling you is you have a horizontal line. Well, what type of formula is a horizontal line? Y equals number. Yeah, y equals a number. Exactly. So, y equals what number? The y coordinate of that point, right? 2 is the x coordinate. That can't be it. It's the y coordinate. So y equals 4. Done. No calculation necessary. It was a little bit stranger to think about, but definitely easy on the calculation. So the next question should be just as easy, the practice one. What does it mean to be perpendicular to the x-axis? Okay, so what type of formula would you expect for a vertical line? X equals number, right? Okay, well x equals what number? -1. There you go. X equals -1. That's your answer for that one. Okay. So that pretty much wraps up to finding the roots of a quadratic function, or I think on your syllabus it's worded a little differently. It's solve a quadratic equation. Okay, it means the same thing. So we're going to be solving quadratic equations in 3 different ways. The first method is going to be factoring. Okay, so I have an example and a practice problem on the factoring method, and then we're going to move to the quadratic formula method, and then we're going to move to taking square roots as our final method. All right. So, example is 2x squared minus 7x equals 4. All right. So the first step is going to be to put the quadratic equation into what I'm going to refer to as standard form. Anybody know or guess what I mean by standard form? Yes?
Yeah, it's not like the ax squared plus bx.
Yes, ax squared plus bx plus c equals 0. So standard form for a quadratic equation is going to be ax squared plus bx plus c equals 0. The important thing is that standard form, there has to be a 0 on one side of the equation. So is this equation as it was given so far in standard form? No. What do we need to do to get it into standard form? Good, subtract the 4. Okay, so we're going to get 2x squared minus 7x minus 4 equals 0. The next thing we should do is identify those three coefficients a, b, and c. So a should be the coefficient that's in front of the x squared, which is in this case what? 2. And b should be the coefficient in front of the x. Yeah, and good, you guys notice you said negative 7 instead of 7. You do include that negative sign. So b is going to be negative 7, and c is going to be negative 4. Good. Okay, now, for the factoring method, okay, what we want to do is we want to focus on the a first, okay? How many different ways does 2 factor?
1.
Just 1. 1 times 2, okay? So we kind of want to start off with something like that. So how are we going to get 2x squared? Well, wouldn't we get 2x squared if we multiplied 2x by an x? Yeah, and that's the only way, right? 2 and 1 is the only way that 2 factors, okay? Now, which of the coefficients do you think we focus on next?
C.
The c, yeah, the c. So the negative 4, all right. How many different ways are there to get negative 4?
2.
2, okay. What ways?
You got 2 and 2 and 1 4.
Okay, 2 and 2, 1 and 4, and one of those has to be negative, which actually gives you more ways. So 2 and negative 2, that's certainly a way, and then you could have 1 and negative 4, or you could reverse that, and you could have negative 1 and 4. Okay, so I think there's 3 ways. And then, on top of that, we have to decide, which we want to put where. And it's kind of a little bit of trial and error, but the more that you do it, you'll get a feel for it. What we want to do is we want to put 2 numbers here and here, okay, that are going to multiply to give us c, but then when we FOIL it back out, we get back to the same equation that we started with. So, anybody want to suggest something to try? Yes?
Ma'am, doesn't the 2 numbers that multiply to get the c, don't they have to add up to equal to b?
They do. They have to add up to b when you FOIL it back out. Okay, and that's not obvious sometimes. Sometimes people think they have the right answer and you try it, but then you need to check by FOILing it to make sure that you do get back that b. So absolutely, the game is you have to pick 2 numbers that multiply to get c, but when you FOIL the expression back out, you get back to what you started with the correct b. Yes?
The tricky part with this one is that the A is not a 1.
Mm-hmm. That does make it tricky.
So
Yes.
that
Okay.
always messes me
So
up.
that's why I said some people don't see it right away, which is why it can be a little bit of trial and error for some people. Okay? So that's why I said, does anybody want to throw out something to try? Yes. You want to do plus 1?
Yes, ma'am.
So then that would mean the other one has to be minus 4. Okay? All right. So I'm going to put a question mark over this equal sign because I don't know at this stage if this factored form is going to be equivalent to what we started with. The only way we're going to know is if we FOIL it back out. Okay? So if we multiply the first terms together, we're going to get 2x squared. And then outer terms is going to give us minus 8x, and then plus an x, and then minus a 4. Okay? Now, does that simplify to what we started with?
Yep.
Yeah, okay, so that worked. Now, if the first thing that you try, now, okay, whether you have a cool shortcut method or you're more guessing, you should definitely FOIL it back out to make sure that it's correct, because if you don't have the correct factors, then you really shouldn't be moving on to the next step, okay? So now we've verified, we're certain that this factored form is equivalent to what we started with. So what should we do next?
Set each parentheses equal to 0.
Yeah, set each individual factor equal to 0. Now I want to point out that this only works, the 0 product rule. 0 is special, okay? There has to be a 0 on the right side for that to work, okay? If I set one factor equal to 0, 0 times the second factor gives me 0, so my equation is still true. Or if I set the second factor to 0, the entire left side still zeroes out. If you have a different number on the right side other than 0, this doesn't work, okay? And some people try it. For instance, what if I tried to factor at this stage here? So far what I wrote is true. Factor out an x, okay? But what I can't do is now, I want to set this factor x equal to 4, okay? So this is going to give me x equals 4, and then this one I'm going to do 2x minus 7 equals 4, okay? Yeah, I could solve those, but would they be the correct answers? No, okay? So, yeah, definitely want to make sure that you have a 0 on the right side before you're trying to set each individual factor equal to 0. All right, so setting the first factor equal to 0, we get 2x minus 1 equals 0. So then that's going to give us 2x equals 1, so x equals 1/2. And for the other factor, we set x minus 4 equal to 0, so then x is going to equal to 4. So our two answers to the quadratic equation are x equals 1/2 and x equals 4.
None of this question.
Oh, whoops.
Negative 1/2?
Yep, I copied it down wrong. Yep. This is called a transcription error, in case you were wondering. Not an algebra error, it's where you write it one way here, and somehow in your brain you write it a different way there. We're very forgiving of that on the GRs. Transcription errors is usually from an A+ to an A. So if you make that same mistake, it's not going to be, so disastrous. But hopefully you don't make that on a GR. All right. So let's see, what would that change in my algebra here? So instead of a 1 here, I should have a -1. And instead of a 1/2, I should have a -1/2. All right. There you go. So similar sort of problem for your practice, okay? Again, I made it a little bit tougher because that A is not 1, okay? These are much easier to factor if your A is 1, but again, I'm trying to prepare you for what you might see later on in the course, okay? So go ahead and same steps. So the first thing you're going to want to do is put that equation 3x squared plus 5x equals 2 into standard form. So make sure you have 0 on the right side. And then you should identify your A, B, and C. And you're going to want to make sure that your factored form has the numbers that multiply to get 3 in front of your x's. And then the game is you want to pick your constants such that they multiply to C, but when you distribute back out, when you FOIL back out, you get the original equation with the correct B. Okay? Match your work that you have so far. The next step is to identify A, B, and C. So hopefully your A, B, and C is going to match mine. And the next part is that brute force memorization, knowing the quadratic formula by heart. Okay, once you apply the quadratic formula, you should have something that looks like this. Now I'm going to stop here for a second and then see if you guys can finish it off, compare answers, and then I'll reveal more. So the next thing I did on the example problem was to simplify the discriminant, which is just the fancy word for everything under the radical. So, oh wait, no, this isn't the one that simplifies. Oh, maybe it's the next, okay. Maybe it's the next one, next sheet. All right, I lied. No, this one does not simplify nicely because 33, okay. All right. Anybody, raise your hands if anybody got this same solution. Oh, excellent. Okay. Awesome. Any questions on using the quadratic formula? It's pretty straightforward. You just have to have that quadratic formula memorized. Okay. So then the final method is going to be using square roots. Now this method is kind of a special case, okay? It only works if one of the three terms goes to 0. So can anybody tell me which of the three letters would have to be 0 for this method to work? A, B, or C? Yes?
Answer B.
The answer is B, yes. So this method, which I'm calling using square roots, only works if your B is 0, okay? So both problems, the example one and the practice run, are that special case where we don't have a BX term, okay? All we have is the squared term and the constant term. So for these, we're not going to use factoring, but we're also, I mean, you could use quadratic formula, right? I said quadratic formula works on all of them. It works on these two, but we can use a method that's a little bit quicker than the quadratic formula. Okay, so first example, 2x squared minus 3 equals 0. So if we're not factoring and we're not using quadratic formula, what do you think we're doing? Yeah. So first you want to make sure that your constant goes to the other side, which is different from the other, right? So we've been putting the equations in standard form so far, so this is where things get a little different. We're actually not going for standard form here. We actually want the constant on the other side. So we want to add 3 to both sides. Then the next goal is to solve for x squared. So to solve for x squared, we need to divide both sides by 2. And then finally, we want to solve for x by taking the square root of both sides. So x is going to equal plus or minus the square root of 3/2. And then we're done. Okay. So go ahead and try the practice problem. This is the one I was talking about. Okay. So make sure, sorry, in the back, what's your name?
Nate.
Okay, make sure that you remind me to explain the simplifying of the radical in case it doesn't make sense, okay? All right, just like the example, instead of putting your equation into standard form, you actually want the x squared term on one side, the constant on the other. Then the next goal is to solve for the x squared. And then you want to take the square root. So, okay, does anybody know another way to write square root of 12? Okay, lots of people, yes?
You can split it up. You can do the square root of 4 times the square root of 3.
Okay, so underneath the square root, we can factor the 12.
Yes, ma'am.
Okay, into 4 times 3.
Then you split them up individually.
Okay, so we can distribute the square root to each individual term in the product.
Yes, ma'am.
Okay, yes. So equals square root of 4 times square root of 3. And then we know that the square root of 4 is 2.
Yes.
Okay. Yes. So that's what I was talking about when I said that sometimes you can simplify the radicals a little further. Okay, factoring is a great method, but you have to have some intuition or maybe some sort of cool method that you learned for factoring. But if you're not so great at factoring or not comfortable with it, that's not a big deal because quadratic formula is there for you as your brute force method. And if you are lucky enough to not have a b term, so not have a bx term in your equation, and you just have a x squared term and a constant, then you can use the method that we just learned by moving the constant to the other side, solving for x squared, and then solving for x by square rooting both sides. Any questions about quadratic equation? Okay, so let's see, what's our next topic? Oh, we're not done. Because, do you have, does anybody see something like this on your assignment sheet?
Yes, ma'am.
Yeah, okay. So, I have this under the quadratic equation section, but it says find the roots of a rational function. Interesting. So maybe the quadratic equation comes up in this somehow? Okay. I mean, spoiler alert, yes, it's going to come up. Okay. So basically, this is like the problems that we just did, but we have some more upfront steps, okay? So we actually have to simplify the equation first before we even see that there's a quadratic equation appearing. All right? So step one is going to be, so if we want to get that into a quadratic equation, do we want denominators? No. Okay, so first goal of getting the equation to look more like a standard form quadratic equation is to get rid of denominators. So any suggestions on how to do that? Okay, multiply, yeah. Okay, so we want to multiply both sides of the equation by something. Yes, basically, here's two options for you. We can either multiply both sides of the equation by the x minus 2, or we can multiply both sides of the equation by the x minus 2 squared. Which is going to give us more cancellation? Yeah, so we're going to pick the larger power denominator, in this case the x minus 2 squared. Okay, because if we only multiply both sides by x minus 2, that's not going to completely cancel out both denominators. But if we multiply both sides by x minus 2 squared, the larger power denominator, then we're actually going to be rid of the denominators completely. So we have x minus 3 over x minus 2 equals 3x minus 1 over x minus 2 squared. So I'm going to multiply the left side by x minus 2 squared. But if I do it on one side, I have to do it on the other side to make it even. There we go. So I've multiplied both sides of the equation by the denominator that had the larger power, in this case the x minus 2 squared. So what's going to cancel now?
The whole bottom on the right side.
On the right side, the x minus 2 squared completely cancels with this x minus 2 squared. Yes.
And
Okay.
one time on the left side.
Okay, so x minus 2 squared divided by x minus 2 to the 1, basically. So it's kind of like if you had, x squared over x, okay? Right? If you have squared on top and then 1 on the bottom, then this should simplify to just x, right? So basically we're going to be left with one of the x minus 2's. And is it going to be in the numerator or the denominator?
Numerator.
It's going to be the numerator. Yeah. Now if it was the other way around, let's say we had x over x squared, okay? You'd be left with 1x, and then where would that be? So if I had x over x squared instead, then my leftover x would be in the denominator. I'd be left with 1 over x, okay? But here I have x minus 2 squared over x minus 2. So I'm going to be left with an x minus 2 in the numerator. We're going to talk about exponent laws a little bit more. So if that's not making sense to you, we're going to kind of circle back to that. But we should be left with 1 x minus 2 factor in the numerator. The 1 in the denominator completely cancels out. And you got to be careful about parentheses here. Okay, so we should have our x minus 2 in parentheses and the x minus 3. And on the right side, the x minus 2 squared is completely canceled out, leaving us with just the 3x minus 1. Okay, so we're a little closer to standard form. At least we don't have denominators anymore. But that doesn't really look like standard form. What would we have to do to put that into standard form?
Distribute.
Yeah, distribute specifically on the left side, okay? So we're going to have to FOIL out this left side. So multiplying the first terms, we get x squared. The last terms, we're going to get minus 3x, and then minus 2x, plus 6. Okay, simplify that a little bit. We're going to get x squared minus 5x plus 6 equals 3x minus 1. Okay. So we've distributed / FOILed out the left side, but this is still not standard form, so a couple more things left to do. We need 0 on one side, right, to be in standard form? So what should we do? Yes?
Subtract 3x and 1.
Okay, so subtract 3x from both sides and then add 1 to both sides. Yep. Okay, so this is going to give us x squared minus 8x plus 7 equals 0. So So we're finally back to where we basically started for the other problems. It took us some algebra to get there though, okay? So we've learned 3 methods to solve a quadratic equation, so it's basically up to you, okay? Does anybody see how to factor this?
Yes, ma'am.
Ah, okay, so we can use factoring method. Sorry. Who is it? Yeah. So how can we factor this?
X minus 7
X minus 7
times X minus 1.
times X minus 1. Okay? And if we FOIL this back out, do we get back to minus 8 for the B? Yeah, because we get a minus X from here and a minus 7X from here, which is going to add to minus 8X. Okay? So then we set each individual factor equal to 0. And then that gives us 2 solutions, X equals 7 and X equals 1. But if you don't like factoring, or if you didn't see how to factor it, guess what? Quadratic formula would have worked for you. Could we have used the square root method, the last one we used, or last one we learned, excuse me? Where you move the constant to the other side and then you solve for x squared? No, why doesn't it work?
You have a B.
Because the B wasn't 0, exactly. So your only 2 methods that would have worked would have been factoring or quadratic formula. All right, so I have a practice problem for you guys to try, but it's very, very similar. So let me kind of recap the steps that you're going to be doing here. So first thing is you want to get rid of the denominators. So you want to multiply both sides of the equation by the denominator with the larger power. So which in this case would be what? The cubed. Yeah, the cubed is going to be the larger one instead of the squared. So you want to multiply both sides of the equation by the y plus 1 quantity cubed. And then you're going to want to FOIL out one of the sides and then go ahead and try to get your equation into standard form and then kind of pick your method that you want. Either factoring method if you can do it, quadratic formula if not, and if you're lucky enough to not have a B, then you can go ahead and try that third method. You get 2. You should get to the equation y plus 4 equals y plus 2 quantity times y plus 1 quantity. So whichever way makes more sense to you is awesome, but you should be able to get to this stage, okay? And then from there, yeah, question?
Wait, I thought you had to the y plus 1 over y plus 1. I thought you had to do it on the other side as well.
It's 2 different ways to do it. So the way that I did it here, I just went ahead and multiplied both sides by x minus 2 squared, and then I knew that x minus 2 squared over x minus 2 cancels to 1 factor of x minus 2, okay? This is another way to think about it where you get the same denominator first, okay? Raise your hands if you were able to get to this stage that I have up here. Okay, awesome. So from there, you just need to go ahead and distribute out the right side, okay? So if you do that, you should get this y squared plus 3y plus 2, which then, to get to standard form, you got to make sure to subtract y from both sides and subtract 4 from both sides, which is going to finally get you to standard form here. And at that stage, you can decide, well, we don't have a b equal to 0, right? So the method of using the square root is off the table. So really, it's either going to be factoring method or it's going to be quadratic formula method. So anybody see how to factor it, or do you have to use quadratic formula?
You have to use quadratic formula.
Ah, you have to use quadratic formula. Oh man. Well, that's why it's such a powerful method, because it always works. Okay. Ooh, that square root of 12 shows up. So you can actually, we learned how to simplify it a couple problems ago, right? So see if you can figure out how to simplify that square root of 12. All right, so I'm going to go ahead and reveal that again. Algebra. Okay, so now if you didn't get to the most simplified version of the answer, that's not that big of a deal. Maybe you were able to get to just here. Raise your hands. Anybody able to get to here? Okay, so some people still working on it. Any questions? It's basically just quadratic equation concept that we learned, but with some additional steps. So if you have similar denominators that are the same factor, maybe with one multiplied by itself more times, then this is kind of a good strategy to simplify. So your first goal is, again, to get rid of both denominators. So we learned two methods. One is to go ahead and multiply both sides of the equation by the larger denominator. The other method would be to first try to get the denominators to be the same with that creative multiplication of 1. In this case, it was the y plus. So now we're really done with quadratic equations. Next is solve literal equations for a given variable. This is going to come up a couple places, okay? It's also going to be big in your physics classes. In fact, they retest you on this in Physics 110, I believe, with an algebra exam in the first 8 lessons or so. Solving literal equations is important to them. It's important to calculus. It's going to come up specifically, for sure, in your implicit derivative section, which is a little bit down the line, but this is definitely a good skill for this course. So what do I mean by a literal equation? What I mean is an equation with more than one letter in it, okay? So this can be a little tricky for students to solve because you're used to having just one letter and the rest numbers, okay? So maybe a little uncomfortable, maybe a little unusual, but I have some steps, a strategy guide that will make this hopefully a little bit more of a straightforward process. So step 1 is going to be to get, well, we're really identifying two types of terms, okay? The terms that contain the variable we're trying to solve for and the terms that don't, okay? So for the first example, I'm interested in two types of terms, those that contain x and those that don't. Okay, but first I actually want to get rid of that too. So we have a, nope, I keep losing my good pens. Okay, a equals x plus y over 2. So if we go ahead and multiply both sides by 2, we're going to get 2 times a equals x plus y. So 2a, does that term contain an x? No, so I'm going to label this as a non-x term, okay? X, well yes, of course that's an x term, it is x. Y? No, okay? So non-x term, non-x term, okay? I want all the non-x terms on one side of the equation, all the x terms on one side. Now this is kind of a simple one, so it seems kind of obvious what I'm saying, but it'll make more sense as we get to harder problems. So we have an x term and a non-x term on the same side of the equation. We don't want that. So which one has to go? The y, yeah. I know, this one's kind of overly simple, so it almost seems obvious what I'm saying, and we're done. I'm actually going to make the next practice into an example. You're going to have a practice on this though, I promise. So this one will reinforce more what I'm talking about. So we have capital V equals xy plus yz plus xz. And what are we trying to solve for? Which letter?
Y.
Y, okay? So I'm interested in two types of terms. The terms that have y and the terms that don't have y. So I'm going to call them y terms and non-y terms. All right? So the y terms have to be on one side of the equation. The non-y terms have to be on one side of the equation. So which side is going to be the y side? Right side, okay. So anything that doesn't have y needs to be on the left side. So what needs to move?
XZ.
The xz, okay. So we're going to subtract xz from both sides. Okay. So that's basically step 1 to solving literal equations, is getting the terms that contain the variable you're interested in solving for on one side of the equation and the terms that don't contain it on the other side. What do you think comes next?
Division?
Not division,
Take out a y.
actually. It's factoring, yeah. The whole point of making one side of the equation all contain y is they all have something in common, right? By design, I put the y terms on one side, so I know they all have something in common. What do they have in common? Y. Okay? So that is a common term. I can factor it out. So on the right side, on the y side of the equation, I'm going to factor out a y, which will leave me with what in the parentheses? X plus c. Good. Okay. Now, once the variable you're trying to solve for is factored, now, yeah, somebody said divide. Now the division is coming up. So to finally solve for y, we have one last step. We need to divide both sides by x plus c. which is going to give us y equals b minus xc over x plus c. Okay. So basically these steps, I mean, there's slight variations on problems, but mostly the steps I'm outlining are going to work on most of these. So just to recap, we want to separate the two types of terms. So since I am interested in solving for y, I want y terms on one side, non-y terms on one side. Then on the y side, okay, I'm calling it the y side, you want to factor out that y so that you can finally divide and solve for y. So, example, okay. Now this one's a little different because we kind of have an initial step before you do the whole separating. If you have a denominator, I would say the first thing would be to get rid of the denominator, kind of like we did here, right? Step one was to multiply both sides by 2. So for this one, our first step is going to be to get rid of that y plus 2. So how do we do that? Yeah, multiply both sides by y plus 2. So we have 3x, what is that, cubed? Yes. 3x cubed times y over y plus 2 equals 4. Okay, and when we multiply both sides by y plus 2, we have to make sure that's in parentheses. So we should have 3x cubed times y equals 4 times y plus 2, that y plus 2 in parentheses. Okay, now, we're interested in two types of terms. Those that have y, those that don't, because it says we're solving for y. Okay? So, we have a y term here, right? 3x cubed y, that has a y in it. So, should we make the left side maybe the y side? Okay. How many terms do we have here? Yeah, it's 2, but it's kind of weird because they're hooked together by that 4. So we actually need to distribute here so that we can truly separate the two terms. Okay, because it's kind of hard to see which one is the y term and which one is not until we actually distribute that 4. Now we see two separate terms. 4y contains a y, but 8 does not. Okay, so we said the left side was going to be the y side, so that means the right side is going to be the non-y side. So 8 can stay on the right side, but 4y has to move. Okay, so we're going to get 3x cubed y minus 4y equals 8. Now we're to that place where we want to be, where the y terms are all on one side, the non-y terms are all on one side. What comes next? Not dividing yet. Factoring, yes. The whole point of making this side all have something in common, which is the y, is that that common thing can be factored out. So because each of these terms on the left side contains a y, we can factor out y. So factoring out the y on the left, what goes in the parentheses?
3x.
Yes. 3x cubed minus 4. Perfect. And now we're ready to divide. Okay, so the dividing comes after the factoring. So we're going to get y equals 8 divided by 3x cubed minus 4. Okay, so one last problem in this for you to try. This is the end of the literal equations. I gave you a little bit more complicated one, but I have faith that you guys can do this. Same sort of steps though. You want to, no, what are we solving for? Z, okay? So it's not going to be y terms and non-y terms. Now it's going to be terms that have z and terms that don't have z. So make sure you have them on the correct sides of the equation, right? Okay? So make sure, so the first thing is to move your terms, get the z terms on one side, the non-z terms on one side, and then your next step is going to be to factor out that z, and then the last step should be dividing. All right, so let's reveal some of these steps. Real quick. Oh, where did my mouse go? There we go. Okay, so let's see, which one did I pick? Oh, I picked the left side of the equation as my z side. If you picked a different side, that's okay. So you can see that all my terms on the left side have z, all my terms on the right side do not have z. Once I've done that, I can factor out z on the z side, quote unquote. And then my last step should just be to divide and solve for z. Okay. So hopefully now with this strategy guide, the fact that there's so many letters floating around is a little bit less intimidating. Hopefully. Okay, does anybody feel a little bit better about this? Okay, good. Now remember, this is going to come up in implicit derivatives again, but instead of solving for a letter, you're actually going to be solving for a thing called dy dx, which you don't know what that is yet, but just try to maybe keep this in the back parts of your brain that solving for something where there's multiple letters floating around, remember this strategy guide, okay? So whatever you're interested in solving for, whether it's x or y or z, or eventually dy dx, you want to separate into things that have dy dx and things that don't, okay? So this same strategy guide is going to come up again later in the course. All right, so moving on to the next objective, we have separate constants from variables. Now this is very appropriate for this course because the reason why we want you to know how to separate constants from variables, anybody heard of an FSQ?
Yes.
Yeah, derivative quizzes, which is coming up block 2, I think? Or is it block 1? I think your first quiz is in block 2.
I think it's at the very start.
The very start of block 2, right? So there are simplification rules on those derivative quizzes. So not only will you be asked to know how to take derivatives of various functions using all the derivative rules we're going to teach you, but to get full credit for your answer, you actually have to simplify your answer. And to get a correct simplification, part of that is putting your answer in the format of constant multiplied by variable expression. So in order to do that successfully, you have to be able to separate constants from variables. So the reason why we're teaching this right now, so hopefully once we get to the derivative quizzes, it won't be brand new to you of how to write your answers for full credit. Now if you do the derivative correctly and you don't simplify it correctly, you could still get, well, okay, let me backtrack. If you do the derivative correctly and you don't simplify at all, you're still going to get credit for doing the right derivative. You're just going to get 75% of the points for not simplifying. Now, if you try to simplify it and you do wrong algebra, so you change your answer completely by wrong simplification, then it actually takes you down to a 0. So we want to make sure we know how to simplify correctly because I don't want any of you guys to be getting zeros on the derivative quiz. All right. So what do I mean by separating constants from variables?
One side of the equation be just numbers, the other side is letters.
Okay.
They're already separated from each other.
Okay. So we want our answers to be basically this format. So we want a constant first, okay? We want a constant first, and then multiplication, and then what's going to go in this box is some sort of variable expression. Okay? The constant must be in front. Okay? This is going to be true for your FSQs. We expect the constant to be in front of the variable expression. All right. So we're starting off with an example of the cube root of 8x. Where both the 8 and the x are under that radical, okay? Now, this is not the only way to simplify it. There's other ways, but I think this is a good kind of strategy guide, especially if this is a new topic for you. It's going to be really helpful in derivatives to actually rewrite radicals as fractional powers. It makes doing what we call the power rule for the derivative a little bit easier. So, does anybody know what is the equivalent fractional power of the cube root? Yeah.
1/3.
1/3, good. Okay, so this is going to be equivalent to 8x all raised to the 1/3. So, exponents, this is one of your exponent laws, okay? Exponents distribute over both products and quotients, okay? So 8x, that's 8 multiplied by x. So we have a power being, or an exponent being applied to two things that are multiplied together. So we are allowed to distribute that exponent 1/3 to each individual term in the product, right? So this is going to become 8 to the 1/3 multiplied by x to the 1/3. So I have distributed the exponent of 1/3 to each individual term in that product. Okay? At this stage, we're already in the correct format, right? Is 8 to the 1/3 not a number?
Yeah.
Yes, times a variable expression. However, not only do you have to put constant first, variable expression second, you also have to simplify the constant. Is 8 to the 1/3 the most simple way to write that? No, the cube root of 8 is 2, okay? So the most simple way would be to write the constant as 2, and then our variable expression part would be x to the 1/3. So basically, we would be looking for your final answer to look like that. Okay? Now, if you really wanted to write cube root of x instead of x to 1/3, that's fine. I'm going to suggest this way. It's easier to read because if you write this, okay, what's the downside of writing it like that? It looks like it's a 2 cubed. It's hard to see if it's the cube root or if it's the cube of 2. Okay? So I would definitely suggest that one. Okay? Strongly suggest that one. All right. So for the practice one, okay, we have a square root instead of a cube root. So which fractional power is that?
1/2.
1/2, okay? So the first thing is you're going to want to write x cubed over 5, okay, that whole thing to the 1/2 power. And in our example problem, we distributed the exponent to a product. It turns out you're also allowed to distribute an exponent over a quotient. So same sort of idea, you want to distribute the 1/2 power to the individual terms, so to x cubed and also to 5. And then from there, you want to get the constant in front and the variable expression second. All right, so see if you can figure out how to do that. If not, I'm going to put some steps up here in a second, but I want to give you a chance to try it on your own. And feel free to get ideas from somebody sitting next to you. That I did here, just like the example, is I rewrote the radical as a fractional power. Okay, so that's nothing new. And then the next thing I suggested was to distribute that exponent to each individual piece in the quotient, so to the numerator individually and to the denominator individually. But then there's something new. Does anybody know how to simplify when you have a power raised to another power? Yes.
Multiply.
You do multiply them together, yes. So some books call this, and I believe our book calls it, the power of a power rule. Okay, so power raised to a power. And you do multiply them together. So if I multiply 3 together with the 1/2, then I can write the numerator as x to the 3/2. All right? But this is not in the format that I wrote here, right? Constant first and then multiplication and then variable expression. So how do you rewrite that?
To the negative.
There's a couple different ways. There's actually, I think, 3 different ways. Okay, let's look at our options here. Okay, all 3 ones that I wrote down would give you full credit. All right, so you can basically just slide the 1/5 to the 1/2 over. So it's basically, right, whether I write the x to the 3/2 here or I write it to the side, that's still equivalent, but now I have the constant first and the variable expression second. So that's one way to do it, okay? So it's almost like you're sliding that x to the 3/2 over. Another way to do it, I heard it, somebody said it, is to rewrite the 5 to the 1/2 as a 5 to the negative 1/2, and then write that first. That's another way to do it. Or, if you like, some people really don't like writing the 1/2 power. If you want to write it as 1/square root of 5, that would give you full credit. All right, we'll do another example, then one last practice. Okay, so our goal is still the same, to get into that format of constant first, variable expression second. But for this one, we have 7 over square root of 3x. Okay, so if we're following the kind of a similar strategy to the previous problems, the first thing is we're going to want to rewrite that radical as a fractional power. So I'm going to go ahead and rewrite this as 3x to the 1/2 on the bottom. And then we're going to distribute the exponent to each individual term in that product. So 7 over 3 to the 1/2 times x to the 1/2. And now we need to get the constant and the variable parts separated, okay? What would be a valid strategy to do that? There's multiple. Slide the 7 over.
So that's 7 and then times 1/3 to the 1/2.
Well, I think I understand what you're saying. Okay, let me see if I understand what you're saying. So Would that be correct?
Yeah, I was wrong. I thought it was
Okay.
just the 7 alone, and then 1 over 3.
Well, so that wouldn't completely separate it because that 3 to the 1/2 is still a constant, okay? I need to get the constants
Okay.
completely separated from the variable part. So I can't just move the 7 over, the 3 to the 1/2 has to come with it because that's a constant too, okay? So I can do this, but I should probably rewrite the 1 over x to the 1/2. Yeah, that's what you were thinking?
Yes,
Okay,
ma'am.
how can I rewrite it?
You just turn it back into a negative exponent.
Okay, so I can say 7 over 3 to the 1/2 multiplied by x to the negative 1/2.
Yes, ma'am.
Does this satisfy our form?
Yes, ma'am.
Yeah, I can go ahead and do that. Perfectly acceptable, right? Constant first, variable expression second. Is it the only acceptable answer? No. Yeah, do you have a different way?
Wait, can you just explain how you got the x to negative 1/2?
Okay. So if you have an exponent in the denominator, that's equivalent to
It's like reciprocal.
not the reciprocal, but the opposite sign. Okay. So if it's a positive exponent in the denominator, it's a negative exponent in the numerator, or vice versa.
Okay.
So what you're not taking the reciprocal of the exponent, you're actually taking the opposite sign of the exponent.
Okay.
Okay? Does that answer your question?
Yeah.
Good. So another way to write it, if you really don't like the 3 to the 1/2, this would be another okay way to write it. Okay? If you really want to rationalize, now, in years past, rationalization of this fraction has not been required. What I mean by that is some people would then have the instinct of just go ahead and multiply by square root of 3 over square root of 3. If you want to do that, you certainly can, but you don't have to. Okay? So this would be another acceptable version of the answer. Okay. So go ahead and try that practice real quick. So we have square root of 2 divided by cube root of 8x. This should be pretty similar to one of the ones we did before, so hopefully it should go quickly for you. Again, one thing I like to do is to rewrite those radicals as fractional powers. So we have 2 to the 1/2 divided by quantity 8x to the 1/3. And then as we've been doing in all of the previous problems, I'm distributing that exponent to both individual terms in the product. And I think from here is where some people might be still having trouble seeing what to do. And maybe some people are starting to feel a little bit more comfortable. But this is a lot like what we have going on here, right? We have a constant in top, and then in the denominator we have a constant and a variable part. So what can we do? Yeah?
This is again about making make it a negative 1/3.
Yeah, that's a great strategy. It's an x to the 1/3 in the denominator, which means in the numerator you would just flip the sign of the 1/3 and make it x to the negative 1/3. Absolutely. Yeah, that definitely works. Okay, so we can do that right here. But our constant, well, so we're most of the way there. We have constant times variable expression. However, that's not enough to be fully simplified. Not only do we have to have constant times variable expression, I should also add something to that. The constant should be, if possible, simplified. So is this constant as simplified as it can be? No.
Would you just subtract the exponent?
Well, a to the 1/3 is 2. I think we discussed that before. Okay. And then from there, okay, there you go. We can apply a law of exponents to simplify this, okay? We have the same base, so these really can be combined into a single term, okay? So if I take my exponent on top is 1/2, my exponent on bottom is 1. So if I take 1/2 and subtract 1, then I end up with 2 to the negative 1/2. So this would be a correct simplified answer, but so would this, if you would rather write it as 1 over square root of 2. Okay? Actually, I think square root of 2 over 2 would be accepted.
Okay.
I think it would, because that would be the rationalized version, yeah. Okay? But notice how both versions of this answer do have constant first and then variable expression second. That's really the thing we're trying to hammer here, okay? So hopefully by the time you get to your first quiz, you're more focused on the derivative rules and this whole constant variable thing is not confusing and you're already a little bit used to it, yeah. So just to reiterate, not only for your algebra assignment, but hopefully you'll kind of remember some words that I said in lesson 2 by the time you get to quiz 1. Your answers must be written in the format constant times variable expression. Constant should always be in front, and they should be as simplified as you can make them, okay? So that's kind of the rules of engagement for your upcoming quizzes. So, our next topic is put equations into a specified form. All right, starting off with an example. Can anybody kind of see where this is going?
Yes, ma'am.
What do you see? Yeah, lots of distributing, lots of foiling going on in these, for sure. Okay. Minus 3x squared, times x minus 3, minus 5. Okay, so our goal is to get this into the format of ax to the 4th plus bx cubed. This is basically standard polynomial format where you have descending order of powers. So you put your highest power of x first and then you go down from there until you get to your constant. So before we worry about that, we need to go ahead and expand this out as much as possible and then combine like terms. So for these ones, these two terms here, x minus 1 and 2x plus 2, we're going to want to FOIL that out. So x times 2x gives us 2x squared, and then x times 2, we get a plus 2x, and then a minus 2x, and then a minus 2. Here we need to distribute the 3x squared, or actually we're distributing the minus 3x squared. So minus 3x squared times x is going to give us a minus 3x cubed, and then minus 3x squared times minus 3 will give us a positive 9x squared, and then we have that minus 5. So once you've expanded everything out as much as you can, now it's time to combine like terms. So the x squared terms, well actually, no, what's our highest power in this? Okay, and how many of those terms are there?
Just one.
Just one. So that one has to go first, okay? So the minus 3x cubed should go first because that's the highest power. Then we do x squared terms, and how many of those do we have?
2.
2. So those get combined together. 11, right? So 9 plus 2 gives us 11x squared. Now we go on to the next lower power, which should be x to the 1, or just the x terms. Oh, the 2x cancels with the 2x, yes. And do we have any other x terms? Oh, we don't.
Not x.
Okay. Is that okay?
Yes, ma'am.
Yeah, not every polynomial has every single power in it. Okay. So all of our x terms canceled out, so we skip that one. All right, so then next comes constants. We have -7, okay? So let me recap real quick. You want to expand out your expression as much as you possibly can, and then you want to combine like terms and order your terms in descending powers of x. So we list our highest power of x first, and then descend down to the constant. So go ahead and try the practice problem, okay? So same sort of steps. First, you're going to want to expand as much as possible, and then combine like terms and order everything in descending order. Okay. So that should give you something like this. And then, are there any like terms to combine after that? No, every single one of the terms is different, so then the only thing really we have yet to do is what? Reorder it, yeah, reorder. So we need to put the highest power first, which it already is, and then the next one should be the cubed, and then the next one the squared, And we don't have a constant here, but that's okay. We don't always have each of the terms, but as long as you order them properly, then that should be fine. Okay. So, yeah, I jumped up in difficulty here. Oh my goodness. Okay. So, the strategy of simplification is going to be a little bit different here. So notice how everything's kind of expanded out already. So here where we had everything in factored form, in order to simplify, notice we had to kind of expand out and then combine like terms. So it's kind of the opposite strategy here. We're actually going to want to factor and see if any of the factors cancel. So let's see. We have x squared minus 9 over x squared plus 2x plus 1. And then we have 3x plus 3 divided by x minus 3. Okay? So we're going to get the most cancellation possible if we can put all of this in factored form, because it's possible we might have a similar factor in the numerator and also in the denominator. There might be some cancellation there. So does x squared minus 9 factor?
Yes.
Yes. Okay. What does it factor into?
It's the difference of 2 squares.
It is the difference of 2 squared, so it's going to factor into x minus 3 times x plus 3. Okay. What about this? It doesn't factor because it's not a quadratic, but can we pull out a constant?
Yes.
Yeah, a 3. So if I pull out a 3, then I'd be left with what? X plus 1. Okay. So now let's focus on the denominator terms. All right, does x squared plus 2x plus 1 factor? Yeah. I believe it's x plus 1 times x plus 1. It's a perfect square. All right, and then we have finally x minus 3. So now that we've factored as much as we possibly can factor, now we're going to see the maximum cancellations that might occur between the numerator and denominator. So what do we see that cancels here? Yeah, the x minus 3s. What else? X plus 1. Oh, but not all of the x plus 1s cancel, just one, right? Okay, so anything else that cancels? No. Okay, so then our most simplified form would be 3 times x plus 3 over x plus 1. Why did I move the 3 in front?
Because you're fixing your shoe. Yes, no.
Because in this class, the habit should be simplified form is constant in front. Okay. All right. Oh.
What if we distribute the 3s?
What if, then that would be okay. Yeah, that would be okay. All right, so there's an extra curveball I threw in the practice. Notice it's not multiplication, it's divided. So there's an extra first step. What do you think you have to do first? Yeah, so it's, whenever you divide by a fraction, you can think of that as multiplying by the reciprocal. So step 1 is you're actually going to want to rewrite this as multiplication of reciprocal. So notice how I'm flipping this second constant. So now that basically puts you at the stage that we were for the example, okay? So once you've rewritten that division as a multiplication by a reciprocal, then you want to go ahead and factor as much as you can possibly factor, all right? So go ahead and try that. X plus 2 factor into.
X plus 2, x plus 1.
Yep, x plus 2, x plus 1, and then I believe this one factors as well.
Yep.
X plus 2,
X plus 4.
x plus 4. And then, kind of like the 3x plus 3, you can pull out a 2 from this. Okay, so you can pull out a 2 from this linear factor here, which would leave you with... So this should be as much factoring as you can possibly do if you can get it to here. And then your goal is to see what cancels between the numerator and the denominator.
Your x plus 2's cancel.
X plus 2's cancel, yep. Anything else?
X plus 1 over the x plus 1
Uh-huh.
cancel out. So
Okay.
that'll leave you with an x plus 4 over 2x minus 3.
All right, so most simplified form should be, okay, and it hopefully, there we go. Okay, so you should have something like that. What kind of simplification are you gonna have to do in this course? This is coming up actually really soon. This is block 1 stuff. So hopefully this will help you if you're not familiar with this algebra. Okay, has anybody heard of a root conjugate?
Oh, man.
No, okay, great, we're gonna learn about it. Okay, so if I have let's say 2 terms, okay? A plus square root of b. Then the root conjugate,
A minus the square.
okay, is the exact same 2 terms. So A square root of b, those are my 2 terms, okay? The only thing that changes in the root conjugate is the sign between them. So my root conjugate would be A minus square root of b. Let's do a different example. How about square root of x plus 1 minus square root of 7. Okay? So to use the root conjugate, at least one of the 2 terms should have a root. Otherwise, root conjugate doesn't really make sense if there's no root involved. So either one or both of your terms has to have a root, and there should be either addition or subtraction between the 2 terms, because otherwise root conjugate doesn't make very much sense. Okay? So here I have 2 terms, at least one of them has a root, and I have either addition or subtraction between. So then the root conjugate is the same 2 terms, but we just changed the sign between them. So my root conjugate should be square root of x plus 1 plus square root of 7. Okay, so that's what a root conjugate is. We have 2 terms, at least one of them has a root, there's either a plus or minus between them, the root conjugate switches the plus to a minus or the minus to a plus. All right, so for our example, we have 2 divided by square root of x plus 7 plus square root of x. All right. Now, somebody mentioned earlier the whole creative multiplication by 1. We're going to use that right now, okay? So the idea is you want to multiply and divide by the root conjugate. Okay, I can't just multiply because then it's not really multiplied by 1. As long as I multiply and divide by the same thing, I'm truly only multiplying by 1. And that thing we want to multiply and divide by is going to be the root conjugate. So here I have 2 terms added together, at least one of them has a root. So what is the root conjugate of this denominator here?
Square root of x plus 7 minus square root of x.
Yeah, square root of x plus 7, and then the plus has to become a minus. We flip it, okay? So square root of x plus 7 minus square root of x. All right? And then we have to divide by the exact same thing so that we're only really multiplying by 1. All right? Now, if you're trying to simplify, well, on this one, I'm only trying to rationalize. I don't think this one simplifies quite as much as some of the others. Your simplification at first should be focused on the 2 root conjugates multiplying together, okay? In the numerator, I'm not multiplying I'm not multiplying the 2 root conjugates together. Only the denominator am I multiplying the 2 root conjugates together. That's where you're gonna get some immediate simplification, okay? Why? Because it's like a difference of squares, right? If I FOIL this denominator together, do you see how the inner and outer terms should cancel? Well, let me write it out. So in the numerator, we're going to have 2 times square root of x plus 7 minus square root of x. And then the denominator, I'm going to get square root of x plus 7 squared minus square root of x times square root of x plus 7 plus square root of x times square root of x plus 7, and then minus square root of x squared. Okay. So because I have that difference of squares, notice my 2 terms here, the inner, coming from multiplying the outer terms and the inner terms together, should cancel. And what happens when I square a square root?
The square root goes away.
Yeah. So whenever the whole idea of multiplying 2 root conjugates together is they always simplify by design. Because for one, the inner and outer terms cancel, and for a second thing, you're squaring all the roots, so those are all going to simplify. So you should always expect a lot of simplification to happen when you multiply two root conjugates together. So the numerator didn't really change much, but in the denominator, let's see, we're left with x plus 7
Minus
here, and then minus x. So we get a cancellation, right? X minus x. So just 7, okay? So this didn't simplify that much, but this is called rationalizing. It's kind of the same thing if you have 1 over square root of 3 and you multiply by square root of 3 over square root of 3. Rationalization just means that you're moving the square roots from the bottom to the top, okay? So what we've in essence done is we started off with a problem where the square roots were in the bottom, but we finished with an answer where the square roots were in the top, okay? In the next one, you'll see that sometimes not only will the root conjugate method simplify things, but it actually might give you some cancellation. Let's see. Okay, let's move back up. So the first thing we notice is that there's 2 terms in the denominator where at least one of them has a root. So we want to multiply and divide by the root conjugate. Oops, I meant to go this way. There we go. So the root conjugate is the same 2 terms, but with addition in between. And then we want to focus on multiplying the 2 root conjugates together, because that's where we're going to get some immediate simplification. So doing that, we notice that the inner and outer terms cancel, because one is plus 3 square root of x plus 2, one is minus. Okay? And then, like I was saying, sometimes you actually get some more simplification of factors. So we have an x minus 7 on both top and bottom. That's really nice. Okay. And then your final, most simplified version and rationalized. Okay, so it's rationalized because the roots have moved from the bottom to the top, and it's simplified because we were able to cancel out that factor x minus 7. Let's see, we're doing our time. We have about 9 minutes left. Okay, so the one, let's see. So we said this one, the second practice problem simplified as much as we could to that there. Last practice problem, our root conjugate should be the square root of x minus the square root of y. So we've just changed the sign in between. And then, if you simplify, you should see that you have an x minus y factor on top and bottom, so those can cancel. So the rationalized version slash most simplified version should be square root of x minus square root of y.
Thank you so much.
You're welcome.
Thank you.
All right. Yes.
Real quick,
Uh-huh.
in the example you just picked up,
Yes.
did you just leave it as 1 over square root x plus h plus square root x?
Okay, so the yes. I mean, it is equivalent.
You just leave it like that?
It is equivalent to this. So we haven't learned this in the course yet, but eventually the purpose of the root conjugate is going to be to evaluate limits. So if I were to take the limit as h goes to 0 of this quantity, okay, there's a method called direct substitution. Essentially, I'm plugging h equals 0. This is stuff you're going to learn, okay? If I let h go to 0, then I would be left with 1 over, this would become square root of x instead of square root of x plus h when h goes to 0, okay? So this would basically become 1 over square root of x plus square root of x, which would be 1 over 2 root of x. So eventually, the reason why you're learning this root conjugate simplification is for the purpose of limits, which is coming up in this first block. So, I mean, you're going to get this in class, but I don't know, some of your instructors may not have time to refresh you on what a root conjugate is, so that's kind of what I want you to be familiar with, so you're ready for that algebra when it comes up. Okay? I want you to understand, okay, at this point in time is, do you know what a root conjugate is? Like if I give you 2 terms, added and subtracted, could you tell me consistently what the root conjugate is? Okay, hopefully you feel more comfortable with that. And then the idea of multiplying and dividing by that root conjugate and then trying to simplify as much as possible. All right, the rest of it will be revealed to you in your course with your instructor, for sure. All right. So the only other things I wanted to go over were common denominators, components for the end of this. So how to simplify terms. We've already kind of been doing this with the separating constants from variables piece, but now we're really going to focus on it. So 4th root of x cubed. All right. So one skill you're going to have in this class is rewriting powers as fractions. And one way to do that is to use the law of exponents. So I can rewrite this as x cubed raised to what power? The 4th root is equivalent to the 1/4 power, okay? And one of the laws of exponents is when you raise a power to a power, then those two powers, do they add or multiply? They multiply. So this would be equivalent to x to the 3/4, okay? Let's try the next one. So cube root of x squared y to the 5th. You're welcome. X times cube root of y. All right, so the first thing is I can rewrite the cube root as a fractional power. So rewriting cube root as the 1/3 power. Then I have x multiplying y to the 1/3 power. And we saw this on previous problems. When you have an exponent that's being applied to two terms that are multiplied or two terms that are divided, then you can actually distribute that exponent to each individual term in the product or quotient. So we can distribute the 1/3 power to both the x squared and the y to the 5th. Okay. You're welcome, you too. And now we have that same power raised to a power situation going on. So we know that those powers are going to multiply together. So now we have x to the 2 times a third, so 2/3 multiplied by y to the 5/3 over x times y to the 1/3. And now we're using a different law of exponents that says that if you have the same base with different exponents, you can combine them by subtracting the exponents from the denominator. Okay, so let me rewrite this just a little bit. So I have x to the 2/3 divided by x to the 1. And I also have y to the 5/3 divided by y to the 1/3. Okay, so if I want to write this as a single power of x, I need to combine the exponents of 2/3 and 1. But 1 is in the bottom, okay? So I need to subtract 1. So my term should be x to the 2/3 minus 1. And then that multiplies y to the 5/3 minus 1/3. Okay, so I'm subtracting the exponent that's coming from the denominator, which ultimately simplifies to x to the 2/3 minus 1 is going to become minus 1/3. Minus 1/3. And then my y is going to be to the 4/3. Yes. Because 5/3 minus 1/3 gives me 4/3. So the most simplified version of that practice problem is going to be x to the negative 1/3 times y to the 4/3. And the other practice problem, did I have another one? Yes. Okay. This is stuff you're going over in your calculus class right now, so I will leave that to your instructors. The last thing I really want to go over is common mistakes, okay? So to hopefully try to avoid them. And we already talked about this a little bit in the quadratic equation section, the whole not being able to use the factoring method if you don't have 0 on one side, okay, and what can happen. So notice that I didn't actually get my equation into standard form, okay? I went ahead and tried to factor without the equation being into standard form, and you'll see this a lot if you're not being careful and you're trying to rush through it. I've even done it when I was really tired and rushed and not focusing, so it can happen to anybody. But we can tell that 7 and 4 are not the right answer, because what if I try to plug in 4 back into this? I'm going to get 16 plus 12, right? 4 squared is 16, 3 times 4 is 12. Does 16 plus 12 equal 7? Yeah, those are clearly wrong. So what did I do wrong? I did not put my equation into standard form before I tried the factoring method. So hopefully you will try to avoid this mistake. Okay, so it is important that you have 0 on one side. Another mistake that I see a lot is, okay, let's see where the mistake happened. Let's see, here I factored out x squared. Was that valid? Am I allowed to factor out an x squared? Yeah, well, how do we know if it's a correct factoring? The way to check is to distribute it back out. So if I multiply x squared by x squared, do I get back x to the 4th? Yes, I do. If I multiply x squared by y squared, okay, so that part's correct. So from step 1 to step 2, we're good. All right, now, can we distribute a square root over a product? Yes, we can. So I can apply the square root individually to the x squared and then individually to the parentheses. So from step 2 to step 3, we're still okay. It's the last step, okay? So square root of x squared plus y squared does not equal x plus y. It's really tempting to do it, and it'd be really nice if it were true sometimes, because then your math would look really nice and clean. But why doesn't this work? Okay, I have said consistently throughout this review that powers can only be distributed over multiplication and division. Okay, where powers cannot be distributed is over addition and subtraction. So notice between my x squared and my y squared, I have addition there. That's what tells me that I cannot distribute the square root to each individual term. Okay? Same thing if I had square root of x squared minus y squared, right? Addition and subtraction are no-nos when it comes to distributing an exponent. So that's where the mistake happened. So if you were asked to simplify this expression as much as possible, where should I have stopped? Step 3, yeah. Okay? All right. Ooh, this is another one that I see a lot. What did I do? Okay, from step 1 to step 2, is that okay? No, what did I do? I canceled the y's. Well, there's a y here, there's a y here. Why don't they cancel? You can only, because it's obvious. Okay, you can only cancel terms between the numerator and the denominator if both those terms are factored out. Okay, is the y factored in the top? No, nor is it factored in the bottom. So I can only cancel a y on top and bottom if it were something like this. Okay, if I had something like that, could I cancel y's out? Yes, because they're both factored. Okay, so some people try to cancel out terms between the numerator and the denominator when those terms are not factored, so then that leads to mistakes like this. Okay, so that's another thing. This one comes up especially on the derivative quizzes. And it's kind of a sneaky error, okay? Because it almost looks like I did it right. Because this is y to the 1 in the bottom, so isn't that correct that I brought it up as y to the negative 1?
Or what's the...
Yeah, what's wrong? It doesn't even look wrong, right? But I promise you, there is something wrong with this.
Do you need parentheses around the same y?
Yes. Yes. So what's happening here is in the first line, where is 7? It's in the denominator, right? Where is 7 in the second line? Yeah, I can't just like put 7 in the numerator because I want it to be, right? It doesn't work like that. But somehow on the quizzes it works like that. Okay, so there's two options here. One is I can write this as 1 over 7 times 1 over y. Okay, that's perfectly valid because 1 times 1 gets me back to the original numerator, 7 times y gets me back to the original denominator. Now I can write this as 1 over 7 times y to the negative 1. And then that's in a form that's nice for taking the derivative. Okay, cool. Totally allowed to do that. If you want to bring the 7 up as well, somebody mentioned this, okay? Another way we could have done it is to bring up the 7 and the y in parentheses with a negative 1. So if you're saying 7y in parentheses to the negative 1, then that's saying that the 7y altogether was the original denominator, which is true, okay? So basically, magic flipping of numbers from denominator to numerator, that's the thing you want to be on the lookout for. All right. Do I have another common mistake? I do. And this is very timely because this is basically what you guys are going over now, which is solving exponential / logarithmic equations. Okay. So the idea is to solve for x, and I've made some very common mistakes. Let's see if I made one from line 1 to line 2. Okay. So I basically tried to apply the natural log on the left side and the right side, because here I go from 10 to ln of 10, right? Okay, so did I do anything wrong on the left side?
Why did you get up there?
Because doesn't the natural log cancel with e?
They might not know.
That's for tomorrow.
Okay. Okay, so this is what I will leave you with. We will solve this correctly. And then we will be done with the algebra review. Some of you are big troopers with algebra. I appreciate your patience. I appreciate your attention, especially with the technology problems we were having earlier. So when you're trying to cancel out an exponential, okay, you need that side of the equation to be the exponential function and nothing else, okay? So that means I have two constants that I really need to be dealt with, okay? This 2 I don't want here, and this -1 I don't want, because natural log of an exponential, those are inverse functions of each other, okay? But if I'm trying to apply a natural log to a product, then I have to use log properties. I cannot just cancel out as written here. So what should I do first? Move over the 1 or divide by the 2?
Move the one.
Move the 1 first, yes. So adding 1 to both sides, I get 11. Okay, now I can divide both sides by 2. Okay. So now on the left side, what's different from the wrong steps that were up there is I'm now going to try to cancel out the exponential because now my left side is just the exponential function by itself with no constants. Okay? So I can take natural log of the entire left side and set that equal to the natural log of the entire right side. Right? You always have to do the same thing to both sides of the equation. So if I take natural log of the left side, I have to take natural log of the right side. And natural log is log base e. I have an exponential of base e, so logarithm and exponential of same base are inverses of each other. They cancel. So what would I be left with on the right, or sorry, on the left side? Just the x minus 5, yes. And on the right side, I still have natural log of 11 over 2. And now to solve for x, we simply add 5. And we're done. Okay, so the moral of the story here is if you're trying to cancel a log with an exponential, you want to make sure that you got rid of all the constants first before you try to make that cancellation. Otherwise, you're going to run into some algebra errors. Yes?
I'm sorry, can you briefly go over what natural log
What a natural log is?
Yeah. Because I know you said it was base
Uh-huh.
e, right?
Okay,
So if you just have the e to the x minus 5, what does that look like in this?
so natural log of x and log base e of x are exactly the same thing. It's just that we don't like to write log base e because it's more stuff to write. Okay, so e to the x is the exponential function base e. Why do I say it's base e? Because the base of an exponential function is basically the number that's being raised to x. Okay, so this is exponential function base e. This is exponential function base 5. Okay, this is exponential function base 2. I can also have fraction bases. Okay, so exponential functions and logarithm functions are inverses of each other, just like the square function is the inverse of a square root, right? They cancel. If I square root something and then I square that, canceling operations, okay? Same idea applies with logs and exponentials. They are inverses of each other, okay? But they only are inverses of each other if they're the same base. So for example, if I take log base 2 of the exponential function with the same base, then the log base 2 cancels with the exponential base 2, leaving me with just x. Okay? Or I can do it in the opposite order. So if I say 2 raised to the log, okay? So basically I'm putting the logarithm function inside of the exponential function base 2. Because they share the same base, I get that same sort of cancellation. So now, do we work with logs of other bases that often? No. Not really, and especially in calculus, we're mostly going to be focused on base e, okay? So the idea is, if I take natural log of e to the x, I know we don't write natural log as log base e, but they are the same base. So that means we get cancellation, so it just leaves us with x. Or we can do it in the opposite order, so we can put the natural log function inside of the exponential base e function. And again, they share the base e, so we get cancellation. Okay, so that's the idea there. Good question. Okay.